Thank you, Hector. So the next speakers of today is Dr. Felipe Abrahão. He's going to talk about AID and algorithmic complex network. Felipe, floor is yours.
Hi, are you hearing me?
Hear you?
Let me share my screen. My sound is okay?
Your sound is okay.
Okay.
And now we can see your screen.
You're seeing just my slide,
Yes.
right?
Yes.
Right. So, may I start?
Yes, you can start. I will give
Great.
you I'll tell you when you have 5 minutes left and 2 minutes.
Thank you very much. Hi, everyone. So thank you very much for this invitation and opportunity to participate in this workshop. In this presentation, I will be talking about algorithm information dynamics and algorithm networks. In particular, the focus is going to be on the relationships between them. I'm going to present an informal and a very high-level overview on some previous results, and then especially propose some future research. So the goal is to give the main underlying ideas here. Right. Okay. First, I think it's important to highlight some motivation gathered from network science. One of the key problems is the pursuit of a theory that could explain why these complex networks topologies, complex in the sense of being heterogeneous, are so pervasive. For example, this is the case of a small diameter phenomenon, the presence of a high clustering coefficient or fat tail degree distribution. One perspective, and in fact the most common actually in network science, is to explain them as a result from optimization procedure. In particular, by selecting some network topological properties of interest and devising algorithms that can generate graphs while maximizing and minimizing them at the same time. Okay. Another perspective that we are exploring is to investigate which of those features would be advantageous. In the precise case, one understands the network as being composed of processing units. That is, a network complex system that processes information. And network complexity, we are going to talk about in the next slides, is crucial, especially for distinguish networked processing from distributed or parallel computation. Thus, in order to evaluate the performance of the nodes, we adopt a game theoretical framework. This is a common approach in distributed computation, although they do not apply the concepts from complexity science and complex networks that we are applying. Okay. So the approach from algorithm information theory has demonstrated advantages in dealing with the problem of network complexity. In particular, for example, it surpasses drawbacks of statistical information, that is entropy-based methods, that Hector mentioned in the previous presentation. One example in recent work, it was shown that employing the block decomposition method for graph summarization in the form of dimensionality or edge vertex reduction outperforms other methods, reducing the network algorithmic complexity while preserving features of interest, like the clustering coefficient edge betweenness and other centralities. So, right. In the case of this paper, we on Mills minimal algorithm information loss, we also shown that the information difference has a quasi-linear worst-case oscillation as the number of perturbed edges increase. In particular, for constructive ones, that is, in the case of information gain, it is linear, as you can see in equation 2. We're going to explain the information difference here in equation 1. The information difference in equation 1 is the difference between the algorithmic complexities of the original graph and the perturbed one. So here we have algorithmic complexity of the graph G with n vertices. And F is the subset of vertices that are being perturbed. In the case here, we have a destructive perturbation, but you could have a constructive one. So here it's just linear, no? And here quasi-linear. Okay. In addition, for Borel normal and dense graphs, it is linear. Every Borel number is dense. It's linear in both constructive and destructive case. So of course, for algorithmic random graphs that contains maximum algorithmic complexity, there is only a linear variation only in this destructive case. In other words, the information gain is always bounded by a constant. Right. In addition, there is a certain class of graphs, in particular dense and logarithmically compressible. K-trivial means logarithmic compressible. Every computable infinite sequence is K-trivial, but not always every K-trivial sequence is computable. So yeah, there is a certain class of graphs that are capable of embedding its whole algorithmic information content in at least one single edge. Anyway, if this edge is destroyed, the resulting graph not only embeds, but also encodes this information here in equation 5. We have here a conditional algorithmic complexity. So G asterisk is the shortest program that generates the graph G. And here we have a perturbation only on one edge. That is a single element. Such a phenomenon may be related to information robustness and evolvability. Why? This is the case because the vast majority of edges in these graphs are neutral information elements or positive information elements. So in other words, the vast majority of perturbations in these graphs can only produce information gain or redundant information. We'll come back to this later. Okay. Right. An interesting future research is that, in fact, BDM can grasp an even larger class of graphs in which such a phenomenon occurs. That is, instead of determined by a prefix or substring, the algorithmic information of the logarithmic compressible and dense graph can be scattered across partitions. And I think this is useful for measuring modularity and distributed redundancy. In the case, an algorithmic information version of modularity and distributed redundancy. For example, the more the BDM diverges from the most incompressible partition, from the one of the most compressible partition, the more each partition will be working as a separated module that contributes to the graph complexity. On the other hand, the more the BDM converges, in particular converges in a logarithmic order, to the most incompressible partition, the more each partition contains redundant information that contributes to the graph complexity. Okay. Yes. Another interesting future research that I found fruitful comes from the discovery of the thermodynamic behavior in algorithmic information dynamics, and also from the discovery of the existence of an optimum reprogrammability point. That is, the reprogrammability of optimum point is a balance in the signature, the information spectra that Hector mentioned, while maximizing the positiveness and negativeness of the elements. In other words, it means that for graphs with algorithmic complexity within this optimum point, local perturbations can alter the most the length of the shortest program that generates that object. This way, one can classify the elements in terms of information contribution for moving the graph toward or away from algorithmic randomness. As you can see in equation 6, the relative impact of single local perturbations becomes negligible as the algorithmic complexity gets closer to the maximum. That is, when the number of vertices tends to infinity. So the impact of a local perturbations on an algorithmically random graph vanishes as the number of vertices increase toward infinity, as you can see here in equation 6. And here we have just one element being perturbed too. So this information difference is upper bounded up to a logarithmic term of the number of vertices. That is why we have the 0 as the lower bound and a constant as the upper bound for this ratio. Okay. Right. So it's not hard to show that the behavior of global algorithmic perturbations works in an inverse way. That is, it is easier to move away from randomness with global algorithmic perturbations than to move away from computability. So in the case, what is the difference of global algorithmic perturbation with respect to local stochastic one that we have shown in the previous slide? It happens that our global algorithmic perturbations are equivalent to programs that transforms the graph, but taking the whole previous graph as input. Then the question is whether there is a reprogrammability optimum point for global algorithmic perturbations. And if so, one could restrict the language or narrow the class of automata instead of analysis on every possible graph, for example, in order to see if it is possible to converge both reprogrammability points. Of course, as you may have noted, the kind of partition self-determinant graph topology, as we mentioned before, were intended to be a representative candidate for this class. It's something for future research to test. Now, speaking in terms of preserving or not algorithmic randomness of the objects, you can see in this illustrative figure, based on the seminal article, that the farther on the right from the local reprogrammability point, local stochastic reprogrammability point, the more you are robust to stochastic random perturbations. But the farther on the left from the global algorithmic reprogrammability point, the more you are tolerant to intentional attacks. Of course, here we are talking about robustness and tolerance in terms of preserving or not randomness. So as a very interesting future research, one key question is whether is it possible to make both reprogrammability points to converge. If they can converge for a certain class of graphs or discrete dynamical system, then this would be something really, really interesting. Why do I think so? Note that if both points can converge, then one will have a local stochastic perturbation having an impact of the same order of a global algorithmic computation. And therefore, algorithmic probability would be maximized by local stochastic perturbation. Maybe it has something to do with program data duality too. Moreover, they will be equally as robust, as tolerant in terms of moving away from randomness. Something interesting. All right, okay. Coming back to the problem of networked processing or network computation, algorithm networks rise as an abstract model for network systems, where the set of nodes is a population of programs, automata, or computable systems in general. And the connections may be taking place in a multidimensional network topology. That is, the multi-aspect graph that defines the multidimensional network topology, which is the one that defines the connection between nodes, can be static, dynamic, weighted, multi-layer, and so on. So here you can see that the algorithm network is a triplet, the multi-aspect graph G, and the population P, and this mapping function B that we are going to talk about in the next slide. Okay. The function B is the one responsible for mapping multidimensional vertices to the space of properties of processing units. Processing units here being called a node. Well, in general, it may be interesting that vertices do not need to be necessarily the units that are processing information. The same way, the network topological time does not need to be necessarily mapped homomorphically into computational time. But anyway, although it's interesting from an abstract mathematical point of view, for the present purpose of net-inspired computing, we're going to talk about later, we are not exploring these non-intuitive functions B. So in our current models, the population composed of programs can be randomly generated, as we present in the model in the next slide, or fixed. The population can also be resource unbounded, for example, Turing machines. That is the case of the model we're going to present, or resource bounded. In the case, resource bounded in the case of more realistic implementable models, which is a work on the way as of now. Okay. The model, this general model of algorithmic networks was intended to facilitate the theoretical analysis of asymptotic systemic behavior, especially for estimating the emergence of many forms of algorithmic complexity. This way, it is useful, in particular, for investigating the presence of phase transitions when the network size grows indefinitely. One thing that eased the mathematical proofs of the results we are going to talk about next, and in fact, allowed the discovery of a new kind of openness for general computable systems, is that since nodes can be arbitrary machines, the random generation of them immediately defines a universal distribution from algorithmic information theory. The other mathematical concept enabling the proofs is to think in terms of multidimensional connectivity. That is, first, one does not really need necessarily to study synchronous and asynchronous populations in separate models. This is because as long as the dynamic asynchronous network is temporally connected, it is equivalent to another dynamic but synchronous network. You just need to fine-grain the time instance. Secondly, one does not need to study particular kinds of multi-aspect graphs and particular multisets of programs as being the population, and how information is processed in these particular algorithm networks. Instead, one can just focus on the network topological properties that they share in common. For example, and a very important one that I'm going to show, is that one can focus on the length of the multidimensional diameter. In other words, focus on the number of hops it takes for the processed information to traverse the multidimensional space. So other feature of algorithm networks, which is easy to show, in fact, is that it reduces any other computable distributed system, and reduces not only within the same time complexity, but also within the exact number of units, that is cells, agents, neurons. This is what we have been calling node complexity. And also it reduced within the same number of connections, that is links or edges. And this is what we have been calling connection complexity. So these two kinds of complexity is one of the reasons we are calling it net-inspired computing. An interesting conjecture to prove true or false, since not only nodes but also network topology can also be randomly generated, is whether there is or there is not a mixed process that cannot be reduced to an algorithm network within the same nodes and connection complexity, and of course in time and space too. On the other hand, it's also paramount, I think, to find or prove which of the distributed automata models emulate algorithm networks as they can for sure, but within polynomial time, polynomial node complexity, and linear connection complexity. Okay. So what can you do with algorithmic networks? Can you prove any new phenomenon? Let's see that. If one compares the algorithmic complex of the networked computation with the isolated computations, it immediately defines a measure of emergent algorithmic complexity. And if this value is getting increasingly positive as the network size increases, then the emergence of algorithmic complexity is unbounded. Then it is a new kind of open-ended that comes from the interaction. That is interaction here meaning information sharing. Thus, it is an emergent phenomenon that occurs as the number of parts increases definitely and not as time goes on. So it is indeed different from open-ended evolution in the sense that open-ended evolution occurs over time as the systems are getting mutated or changed by the environment. For example, when the number of successive mutations interspersed with selection increases indefinitely. But in fact, there may be a more abstract interpretation of evolutionary open-endedness as being a particular case of emergent open-endedness and vice versa. Anyway, not explored yet. Other important feature of emergent open-endedness is that it does not depend on the observer. In the precise sense that every observer within the same computational class of every possible node will eventually experience the unlimited increase of complexity. And this holds in principle. Right? Let's go to the model then. One type of algorithmic networks we prove emergent open-endedness to exist is in the model of local optimization of fitness values. In particular, we use busy beaver imitation game. In these algorithmic networks, the unbounded emergent increase of fitness values is directly equivalent to the local emergent open-endedness. That is, local emergent open-endedness is the one that occur at the level of the nodes only. And then at the level of the nodes, we estimate an expectancy for the average value. Here, we are not considering the output of the network as a whole. This is the reason we are calling it local. In the last slide, we'll come back to this problem. This way, we showed that pervasive network topological properties found in real-world networks are sufficient for triggering emergent open-endedness. In particular, the small diameter, a small multidimensional diameter, or for monoplex networks, the classical diameter, or fast cover time. Fast cover time is of special interest in the case of dynamic networks. In the case of the multi-aspect, the graph is time varying. Another interesting case we found emergent open-endedness to occur was in the susceptible contagion, in the famous case of scale-free network. In particular, it is a Barabasi-Albert network. These results and models are what we are calling net-inspired computing. More precisely, it is the usage of complex networks phenomena to, more precisely, the network-inspired computing is the usage of complex network phenomena to compute irreducibly harder problems in lower computational class. So here in equation 9, we have, this is the expected emergent algorithmic complexity or algorithmic information. It's average over each node, and C is the number of communication rounds, and W is the network input that is available to every node before the computation starts. So here is allowance bound. We actually study allowance bound for the expected emergent, local expected emergent algorithmic complexity. Here we have this is in fact allowance bound for the partition of the nodes with maximum fitness. And omega, in fact, is a conditional and a communication round bounded version of the halting probability that emerges in the proofs as a normalization constant. And you can see that it works like a threshold for the emergent algorithmic complexity to go to infinity. So in fact, this whole inequality is a lower bound for the emergent algorithmic complexity. The halting probability is just an upper bound for this threshold. Investigation for a tight bound for this threshold is a research underway. Okay. So future research. As said before, we have established results for the local version of the emergent algorithmic complexity. However, taking the outputs of each node in a joint manner is totally distinct from average of each node in terms of algorithmic complexity. Here we have the reason of studying these two phases in which an algorithm network may belong to, the convergent phase and the topological phase. So the convergent phase will be the one in which the information of the networked population as a whole is dominated by the information of a subset of the isolated population. This idea of convergent phase was actually given by Mikhail Prokopenko. Algorithm networks in this phase were already indeed proved to exist in the results we mentioned before. So this is the easy part, that is to show there is an algorithm network to belong to the convergent phase. On the other hand, the crucial problem for future work will be to prove there are algorithm networks in the topological phase. In the topological phase, the information of the networked population as a whole would be dominated by the information of the topology itself. And note that it's not going to be dominated by the information of the whole population. Even if one's taking into account the joint algorithmic information of the whole isolated population. So the global emergent algorithmic complexity in the topological phase is therefore much larger than the global emergent algorithmic complexity in the convergent phase. The clue for this problem, I think, is that in random generated populations of programs with exponential size compared with the network input size, the joint algorithmic complexity of the whole isolated population only grows quasi-linearly. However, the algorithmic complexity of the network topology can grow exponentially with input size, as we see for algorithmic random graphs. And it grows quadratically with the population size. In other words, incompressible network topology may contain information to be harnessed as an oracle by the nodes. So here we immediately get the need to investigate multidimensional network complexity. What we having found in recent work is that one cannot straightforwardly extend algorithmic information of graphs to multidimensional networks in the general case, as there will be some counterintuitive phenomena. As we proved, there are cases in which one can expect to have unlimited distortions of algorithmic complexity when you go to the multidimensional case. So what I found to be very interesting, fruitful then, is that BDM and algorithm information dynamics can in fact be an already fine-tuning method for identifying the localness which defines the convergent phase. So a fine-tuning method for identifying the convergent phase, not only in simulated algorithm networks, but in distributed systems in general. For this purpose, for example, one can compare the BDM of the small sub-networks and check which of these keep having a BDM of the same order of the global algorithmic complexity of the network. So, finally. One underlying idea of defining these two phases is that evolutionary processes applied to algorithm networks can move toward or away from these phases. Although note that emergent openness is not an evolutionary phenomenon per se. So algorithm information calculus together with algorithmically probable mutation can reveal that perturbations on edges or nodes can only contribute up to a logarithmic term in the algorithmic information of the whole distributed system. Just this way, they can only move gradually between these two phases. On the other hand, perturbations that manage somehow to land onto communication protocols can produce faster jumps between the two phases. Just remember, the communication protocols are the information sharing strategy of the whole population. So finally, it's interesting to mention that initially algorithm networks was intended to tackle the problem of evolution of population initiating metabiology by employing the results on algorithmically probable mutation from the article by Hernandez Orozco et al. Then after this, it came complex networks. So yeah, in fact, the motivation, the first slide came after. This is, I mean, the motivation gave guide the need to explain the pervasive presence of some network features. That was it. Thank you.
Thank you, Felipe, for the nice talk. So now we have time, a few minutes. If you have any question, please post it in Q&A. There is one question. Can you see that, Felipe, or you want me?
A preprint of which results? What is future research? There is not. It's on the way, but let's come back to the slide here. The paper on minimal algorithm information was submitted recently. And let's go to the model. Yeah, so the article proving the small diameter phenomenon of fast over time works to generate emergent openness was published already. And the other article for the contagion of the fittest in scale-free networks was also published. Yeah, this case of multidimensional distortion in algorithmic complexity is also a preprint. So.
Okay, if there is no other question, thank you, Felipe, again.
Thank
you.
The
next talk for today is AID in machine learning and machine learning in cellular automata, given by Dr. Santiago Hernandez and Dr. Jürgen Riedel. So floor is yours, Santiago.